Hello, 8 Purple. Welcome. I have a riddle for you. And the riddle is this. If a clock is at 12 o'clock noon, how long will it take? And the hands are overlapping, right? The hour hand is pointing up at the 12 and the minute hand is pointing up at the 12. How long will it take for the hour hand and the minute hand to overlap again? So think about that for a second. Pause if you want to really think about it. I'm about to reveal the hint, so if you want to think about it without the hint more, go ahead. All right, here's the hint. Just a clock face, but it might help you visualize it a little bit better. And now I'm going to reveal the answer. So if you want to think about it, hit pause and think about it for just a minute. All right, here's your answer. If a clock is at 12 o'clock noon, how long will it take? Exactly 1 hour, 5 minutes, and 27 seconds. Because the next time they'll overlap is the hour hand will have to go around once to get to the 1 o'clock. But in just 1 hour, the minute hand will be pointing at the 12. So that minute hand has to go a little bit more. It's got to rotate a little bit more to point to the 1 in order for the hands to overlap again. And this is similar as to why the moon rises later each day. So in our analogy here, the minute hand is Earth's rotation and the hour hand is the moon's change in orbit. It takes more than a full revolution of the Earth. I should say rotation, full rotation. Let me change that actually, that is incorrect. Rotation. It takes more than a full rotation to see the moon rise the next day. So let me explain that visually. So here, first of all, what moon phase is this? Anyone know? It is a waxing gibbous. And that's actually what's happening right now as you're watching this video. We're in the middle of a waxing gibbous. And in about 4 days, 3 days, we'll be at a full moon. So right now, our position on this red dot means that we won't see a waxing gibbous until about right there, which might be like 3 o'clock-ish, maybe 2 o'clock. And so as the Earth rotates, that waxing gibbous would be directly overhead around maybe 9-ish, 8:39 or so. And then we'll rotate out of its field of view sometime in the early morning hours, like 2:30ish or something like that. Now, as the Earth rotates, the moon just doesn't sit there. It moves very slightly. It's going to revolve around us at a very slow pace. So in a 24-hour period, it might move to there, right? It takes 29 and a half days to get all the way around. So it makes sense that it moves about a little bit over the course of a 24-hour period, which also means that this is going to change as well, right? And so now when we get to 2:30, where we were yesterday, we're no longer able to see the moon again. We've got to rotate a little bit farther in our Earth's rotation in order to see the moon. And so that extra rotation translates to about 45, 50 minutes. I forget the exact time, but it's about 50 minutes of a delay as to why we have to rotate a little bit farther to see the moon rise the very next day. All right, so before we get into our next thing that we're going to learn about, I just want to recap the patterns that we have examined that have to do with the moon. The first one we looked at was moon phases as seen from Earth. This is a pattern that you may have visited in fourth grade. It's pretty straightforward, and we get to see it every day pretty much anyway if you look up at the sky. So our cycle begins with a new moon, and then the illuminated side, the side that reflects light towards us, it grows with each passing day until we get to a full moon, and we call that waxing. And then once we're at a full moon, it starts shrinking, but it shrinks from the right side as well. So that process is called waning, and we end up with the left side of the moon mostly lit right before the new moon comes and the cycle is reset. The next pattern that we looked at was looking at moon phases, but instead of looking at them from our perspective here on Earth, we looked at them as seen in orbit. And what we notice is that half of the moon is always illuminated, unlike what we see here, where it looks like a full moon is illuminated, then half the moon is illuminated at the quarters. In reality, the moon is always half lit, but only a certain segment of it is reflecting light back towards us. We notice that it waxes in the first half of its revolution, and then it wanes in the second half of its revolution. Crescent moons are always going to be when they're on the side of their orbit between the moon and the Earth. And then gibbous moons are always on the back side of the orbit. So when the moon is on the far side of the Earth from the sun, you'll have a gibbous moon. And when it's on the side of the Earth that's closer to the sun, you'll have a crescent moon. We can summarize that pattern in this diagram that we made, where you can identify the moon phase by just knowing whatever quadrant it's in. So if your moon is up here, that would be a waning gibbous. If it's down here, it would be a waxing crescent. If it's up here, it's a waxing gibbous, and then down here is a waning crescent. The third pattern we looked at was the relationship between the moon phase, the position, and the time of day. Um, And the basic pattern is that the rise equals the zenith minus 6 hours. So let's get this thing right. Let's try to set up this a little bit cleaner. If we have a full moon that's out at midnight, so that means that it's directly overhead at midnight, right? That means it rises at zenith minus 6 hours, which would be 6 p.m. The set is going to be the zenith plus 6 hours. So if we go 6 hours into the future, that's when we rotate out of the field of view of the moon at 6 a.m. The mid-rise, which would be when the moon is kind of it's been in the sky for a little bit, that would be the zenith minus 3 hours, and the mid-set would be the zenith plus 3 hours, like that. So gibbous moons are out more at night than during the day. Crescent moons are out more at day during the night. And one way to remember this, or one way to kind of solidify this pattern, is that the greater percentage the moon is illuminated, the more time it spends out at night. So when you have a full moon, it's almost out exclusively at night. And when you have crescent moons, they're out almost mostly during the day. Today, we're going to look at patterns in the moon's altitude throughout the year. And I think this is actually my favorite pattern in the whole year. It's not like it's that amazing or beautiful or whatever. It's just a really cool pattern that you would never ever think to look at. But because it's there every day, you can always see it and you can be reminded of it. And I just think it's really, really elegant. And there's these cool things that kind of correspond to it in the future. So what we have coming up with the remaining basically 2 weeks here is we're going to do moon elevation this week and eclipses, and then next week we'll do tides, and that should kind of take us to the end of the year. So let's look at what I mean by moon elevation. Just a couple of key terms that you should be familiar with by now. Celestial altitude refers to how high an object is in the sky it appears. It's not measured by distance like a skyscraper would be or a mountain. It's measured by finding the angle between the object and the horizon. The meridian is an imaginary line that divides the sky in half. It separates the eastern hemisphere from the western hemisphere. An object is at its highest point when it crosses the meridian. For any location, the meridian can be defined as noon. So when the sun is at noon, that means it's crossing the meridian, and it's about to move into the western half of your sky. All right, just so you can kind of visualize that, this line here that's kind of arcing up and going across, that's the meridian. That separates the eastern half from the western half because it connects north and south. Um, so what happens to the sun's altitude and its path through the sky throughout the year? Well, we looked at this pattern when we did the seasons chapter a couple of weeks ago, but basically it looks like this. So if here's your observer and you're looking south this way, this path right here would be the path that the sun takes during wintertime. It's very shallow and low in the sky. In your fall and your spring, it's going to be a medium high sun. It gets a little bit higher, then it comes back down and goes lower. And then in the summertime, it takes a very high path across the sky. This might even be a better view. This is the same concept, but just now you have the point of view of the observer and you're looking south. So the sun always rises in the east and sets in the west. But in the wintertime, it takes this nice low path across the sky. On our equinoxes, it's somewhat in the middle. And then in our summertime, which we're about to have, by the way, in about 20 days, 19 days, it takes this nice, really high path across the sky. If the sun has not yet crossed the meridian, we say it's ante meridian or AM. And once the sun has crossed the meridian, we call it post meridian or PM. So that's where those abbreviations come from. It all has to do with the sun's relative position to the meridian. All right, so let's make a prediction. We know what happens to the sun's altitude throughout the year. That's pretty straightforward. It's low in the winter, high in the summer. What happens to the moon's altitude throughout the year? Does it follow the sun's altitude? Is it the opposite of what the sun does? Is it neither of those two things, or do you have no idea? Well, take a minute, think about it. Maybe make a prediction. Maybe you have, if you're selecting three, then maybe you have an idea of what it does. If so, maybe jot it down really quickly, and then we're going to continue on with the lesson, and you'll see if you're right. All right, so first off, what season is this? So here's our sun, and here's our Earth, and we can see that the northern hemisphere is tilted away from the sun, which means it is not receiving direct sunlight. So it must be winter. And in order to have a full moon during winter, we've got to put the moon in this part in its orbit, right? So if it were over here, that would be a new moon, and all this light would be reflected back towards the sun. So in order to have a full moon, it's got to be over here. So if we're tilted away from the sun, but we're tilted towards this moon, how would it appear in the sky? All right, let's go 6 months later. What season is this? We're tilted towards the sun now. That must be summer. And where would our full moon go now? Well, if it were here, that would be a new moon because it's between the Earth and the sun, and all of that light would be reflected back towards the sun. So we're going to move it in its rotation. Here's a first quarter, a waxing gibbous, and here's a full moon. So here we're kind of tilted away from a moon, right? We're tilted away from a full moon. So I wonder how it would appear in the night sky. How does the sun appear when we're tilted towards it? Think about that for a little bit. All right, so knowing what you do about how the sun changes altitude, how do you think the moon's zenith altitude will change throughout the year? This is what we're going to explore in our lab today, and probably tomorrow we'll tie it up. So today is all about looking at data and making observations, and then we'll wrap it all up and I'll do a quick little presentation, and I have this amazing video to show you guys tomorrow that kind of explains exactly what's going on. So what you'll do with the rest of today is you're first going to open up this I don't know if I'll make a copy for you or just a shared version of this, but this is a series of data tables based off of the months, and the months are located down here in these tabs. So January, February, March, April, May, all the way down. And in each month, you have what the moon is doing as far as its zenith altitude for that day, how high it gets that day, and the sun's altitude. So these are the altitudes that both of these objects would have when they cross the meridian. And in addition to their altitudes, I've labeled the phase of the moon. So here's a third quarter, then would be a new moon. So all this time it would be a waning crescent. And then here we have a new moon, then a waxing crescent, a first quarter, then a waxing gibbous. A full moon would then enter into a waning gibbous. And to the right of each data table is a graph. The blue line represents the moon, and the red line represents what the sun is doing. Now, typically, what I would normally do is I would have you guys break up into groups, and you would just be given this data, and you would have to graph what the moon is doing, and then stitch together your month's worth of data, your graph, with everybody else's. But obviously, that'd be very difficult in this scenario. So instead, I'm giving you guys the data and the graphs, and I'm going to have you do something else with that information. So what I want you to do first is just kind of flip through these months and see if you notice any strange patterns. Um, by the way, this data is from 2014. It's not reflective of this year's moon phases, but the trends of what the phases do is the same. So, for example, so what that means is if you go to June, this isn't these moon phases aren't going to line up exactly with what's happening in our June in 2020, but the concept of their altitude will be the same thing. So anyway, yeah, flip through these and then kind of just look for patterns and see if you notice anything. It kind of sometimes helps to go chronologically, like January, February, March, April, May. And then next, the second thing I want you to do today is with this information, open up a copy of this. Now, you may want to print this out. You can enter the information digitally, but it's a little bit tricky to do the graphing unless you're really good with adding points and drawing lines digitally, maybe with Cami or something like that. Um, but it might work best to print it out and then scan it back in. So what I want you to do here is for each of the phases in each month, write the altitude. So for example, January, let me go to January here. January has the new moon is at 30.1. That's the altitude right here, 30.1, right? And then I'm going to go to the first quarter, which is down here, and that's 61. So I'll write in 61 there. The full moon, its altitude is 63.4, 63.4. And the third quarter moon that occurs in January is 42.4. It doesn't matter if they're slightly out of order. I just want to get the altitudes for each phase. It will become apparent why that is in a little bit. One mistake that you might make is to record the information in this column, but this is for the sun. You will not be recording this information. Make sure that you're recording information in column B. That's the most important thing. So once you're done with January, move down to February, March, April, May, all the way down to December, and you get the idea. Once you have these tables filled in, um, you're going to come down and graph that information down in this line graph. Now, because there are 4 phases, that means there are going to be 4 lines. So make sure you use different colors to represent the different phases. So for example, you'll have the first line. Well, for example, let's do this. So here's our new moon for January. So in one of my colors, I would come down and I'd plot new moon. It would probably make more sense. It would make sense to graph each phase individually. So once you get all the data filled out, graph all the information for new moon, and then you'll be done with that line. Then go back to the beginning in January and graph all the information for your first quarter. And then let me zoom out so it makes some more sense. Yeah, and then go back once full moon is all filled in. Go back here and graph your line for your full moon, and then do the same thing for your third quarter. And something interesting should show itself. The only other thing I want to draw your attention to is the colors on the graph. I highlighted the regions to correspond with different seasons. So this is for the most part, that's winter, this is spring, summer, and then fall. Okay, once that's done for today, I want you to go to the exit ticket. The exit ticket is pretty straightforward. All I want are 3 observations that you've made. No big conclusions, no big math or figuring stuff out. All I want is you to explore these data tables and these graphs right here, and then fill in this table and make this graph right here. And then from that data and those graphs, 3 observations. Okay, thank you for watching. If you have any questions, please give me a shout or an email, really. That would work better. All right, bye.